Hello students. In this video, we're going to solve a critical problem of our game. Right now, our game will run slow on slow computers, and it will run fast on fast computers. And it will run just right on those computers that are right in the middle, I guess. No, this is bad. This is really bad. We have inconsistent gameplay on different machines. Our game is based on frames per second. So on a slow computer, maybe if it's only running 20 frames per second, our game's going to run slow. And on a computer that is really fast, running at maybe 60 frames per second, our game will run faster. We do not want this inconsistency. So we're going to switch our game from a frame-based system to a time-based system, because on a slow computer or on a fast computer or on a computer that is somewhere in the middle, 1 second is 1 second is 1 second. Time is the same. And so switching from frame-based to time-based will solve all of our inconsistency issues. This will also allow us to create what is known as a ramp. We will use a ramp to scale up the difficulty of our game as time advances. So the longer we play the game will get harder and harder and harder. And it will transition in a nice, smooth manner rather than spiking in difficulty. So let's head over to the computer screen and we'll dive right in. So I have lesson 5, our delta time and difficulty ramp lessons starter file open right here in vscode.dev. I'm going to minimize my browser and I am going to open that file directly here so we can see our file in the browser. All right, so let's see what we got. Ooh, right away, I see we've got some stuff in the HUD. We've got like a time of 0 seconds. So oh, and then automatically my health just drops away. Do you guys see that? So I'm going to restart the game. I got full health. And no, I have no health. But I'm not dead, which is weird. Whoa, I'm not dead. And I also am zooming all over the screen. I'm moving weird. My movement system is broken. My health system is broken. My light's not shrinking anymore, so that's broken. Basically, anything that was changing per frame, right? Like our movement, my health, my lights, all those systems are busted. And the reason why is because we are switching from frame-based to time-based. So we've got to do a little bit of work here. So let's head over to our code and let's dive right into lesson number 5. Mission 1, it says add the delta time variable and clamp it. Okay, so, well, let's just see. Before we get there, what do we got in our student edit zone, right? We have these variables. Oh, it looks like my player speed has changed because my player speed used to be 4 pixels. It was 4 pixels per frame, and now it's been changed to 240. And if we think about this, 4 pixels per frame at 60 frames per second, assuming 60 frames per second, if I multiply 4 by 60, I get 240, and the frames will cancel. And so this is now in pixels per second. So instead of moving a certain amount of pixels every single frame, and the frames could be different on slow computers or fast computers, we are now going to move 240 pixels every single second. And that's 1 single second is the same on every computer. And if we look, what do we do? We did something similar for our health drain per second. It used to be 0.33 health per frame. Multiplying that by 60 frames per second, we get about 20 health per second we're going to drain, and about 10 health per second we're going to regenerate. If you also notice, this is interesting, we commented out our light shrink rate of 0.21. And the reason why, first, that was in frames, so we're probably going to have to implement a time-based, pixels per second like we did up here. But also, our light shrink rate isn't going to be constant. We said we're going to build something called a ramp that is going to increase the difficulty of our game. One of the ways we can increase the difficulty is making our lights shrink at a faster and faster and faster rate the longer we play the game. So we don't want to define this as a constant anymore. In fact, if you look here in mission number 5, we've got some ramp constants that we got to define, and it looks like we target our light shrink speed here. So we'll definitely look at that and work at that. And then let's look at what we got for our gameplay variables. We've got something called, I guess, runtime seconds. We haven't looked at that yet. And we've got variables for our ramp here, our light shrink rate, our enemy spawn interval, and our enemy speed multiplier. So we'll take a look at all those. But let's go to mission number 1. Now that we have some familiarity with what we're doing in this new time-based system, we need to set up our delta time. So what is delta time? Delta time is a built-in variable that stores the number of milliseconds that have elapsed since the last frame that has occurred. So it's basically how long did it take for one frame to process on your computer. And that gives us milliseconds. But you know what? We don't like milliseconds. We like seconds. And so to convert milliseconds to seconds, you just simply divide by 1,000. Now, we are going to create this delta time variable. We're going to use it. We're going to create a variable called dt, and we're going to build it from this delta time variable. Right now, dt is just set to 1. So this is saying 1 second has elapsed since our last frame. That's not true at all. We are going to use the built-in delta time variable to get the number of milliseconds that have elapsed since our last frame. But that's milliseconds. Ew. So if we divide by 1,000, we now get seconds. Okay, so this looks pretty good. Except there's something else we got to do here according to this mission. It says clamp it for larger values. So imagine if our game suddenly, like if our computer suddenly slows down and a frame takes much longer to process, then this numerator is going to be much bigger than it typically is. And when that happens, this dt variable will be much bigger than it typically is. And that could cause problems for us if we're going to try to build something on a time-based system. We want our time to be consistent. So what we're going to do is we're going to set a largest value that we'll use. And if it goes beyond this largest value, then we will not use it. We'll just use this upper limit. And the way we're going to do this is with the minimum function. So it's kind of weird that we're using the minimum function to set a guaranteed largest value. But let me explain how it works. We're going to say 0.033 is our lowest possible value, and this could be our whatever like our highest value is. So the min function, I'm sorry, I said that wrong. The min function is going to basically pick between these two numbers whatever is the smallest. So if delta time is like super duper small, let's just say it was like, I don't know, 100 milliseconds from the last frame. If I do 100 divided by 1,000, it's 0.1. So actually that was pretty big. I'm sorry. So this is big, right? That's a big spike. So you could see we're going to use 0.033 as our delta time. So we're going to use 0.033 because that's the minimum of that. But imagine now if, I don't know, like 2 milliseconds has elapsed divided by 1,000. Well, that's 0.002. So now the minimum is this value right here. So this just prevents, it's like a safety. It prevents spikes in our gameplay, lags in our gameplay. So we've got this DT now. Wonderful. So if we look at mission number two, which is right here, it is during when our game mode is set to play. It says update runtime using the delta time and pass DT, our DT, into update functions that require time-based behavior. All right, so we got this variable called runtime seconds. We saw it earlier, right? We saw runtime seconds, and we're adding 0 to it every frame. I don't know. I think runtime seconds is probably going to control this right here. Since we're adding 0, it's never updating. So let's add 1 to it. I don't know. Let's add 1 to it. Let's see what happens. Let's experiment. Whoa! Our game has been running for 250 seconds, 300 seconds, 350, 400 seconds. I don't think that is accurate time. That's not right at all. What is that? That's not showing time. You know what this is showing? We're adding 1 every single frame. Remember, this draw function, this built-in P5 draw function runs every single frame. So every single frame, we're just adding 1. That's showing the number of frames that has elapsed. So right now, I've gone through like 1,000 frames right now. We don't want that. We want time. So we're going to add the time that has elapsed since that last frame. That's our DT variable that we created. So if I add DT to our runtime seconds, now this is an accurate representation of time for our game. I have been playing the game for 6 seconds. Whoa, but all of our systems are still a little wonky. My movement system does not work. My health system's not working. The light shrinking is not working. The reason why is all of those systems require time-based movement now. They were all based on frames. So if I just scroll down, let's go look at those functions really quick. if you look at update player, right here, it needs DT. It needs to know how much time has elapsed. If I look at update lights, it needs DT. It needs to know how much time has elapsed. And update health needs DT to know how much time has elapsed. So what we have to do inside of our draw function where DT exists, we have to pass that information to those functions. So inside of update player, I'm going to pass DT. Inside of update lights, I'll pass DT. And inside of update health, I'll pass DT. Mission 2 is now complete. We are using that DT variable to update our runtime seconds, and it is now going to the functions that need it. Of course, we're not using it yet in those functions. We have, oh, actually, look at that. Our health system, just by giving the health system the DT that it needed, that reference to time, the health system is now working. I'm draining. If I can get back in the light, I'm healing. So that's working wonderfully. But our movement system, oof, broken. And our light shrinking system, also broken. So let's go see what mission 3 has us doing. Maybe it's going to fix one of those systems. And it is. It's going to have us fix the update player function. We have to have player delta time. So we're going to apply our DT that we just got to our player movement to ensure that our movement is consistent across all of our different frame rates, no matter how fast or how slow our computer is. So we've got to target this relationship. So I'm updating my player's X position, figuring out how far we need to move them in the X direction by taking speed and multiplying by their move direction. So remember, move direction we are getting from our get input direction function, so which is right below it. And we have two variables, dx and dy, that we're returning. And those are either going to be -1, +1, or 0, depending on the direction that we are moving in. So really, if we think about it, this is like distance, how far we need to move. And this is like the direction of our speed. And this is the size of our speed. So I'm going to go to the whiteboard here just quickly, and we're going to just quickly talk about a physics equation that describes the relationship between distance, speed, and velocity. We often can say that the average speed of an object or the average velocity of an object is a measure of how far it goes in some unit of time. So if I just multiply both sides by t, I multiply by a t over here, zoop, zoop, the t's cancel, and I multiply by a t over here because what we do to one side of the equation, we have to do to the other. This gives me d is equal to v times t. Now, let me expand this. We got a little bit more room to work with. What is d here? Well, d we just saw is our player's x position. So that's going to be like, we'll do it for the horizontal, player.x. What is v? Well, v has two parts. It's got a direction. The direction is going to be move direction dot dx. And then it's got a size, and our size is player speed. So both of these represent, when you combine them, represent something called the velocity. The velocity has two parts. It's got a direction. Do we want to move left or right or not at all? So -1, +1, or 0. And then it's got a size. How fast are we going to move in that direction? So we've got the d, we've got the v, we just need the t. We've got to multiply by some time interval. What is that time interval we are going to multiply by? We are multiplying by dt. That dt that we passed into this function that it needs in order to move from a frame-based system to a time-based system. We've got it right here. So we just need to update these equations to use that dt. We're going to say, hey, you're moving this fast in a given direction and you have this much time to move. Go figure out how far you can move. And we'll do that in the x direction and in the y direction. Doing that, just those two little fixes, our movement system should be fully operational. And it is. So our movement system is fixed. Our health system is fixed. We just need to fix our light system. So let's go to mission number 4. Mission number 4, no surprise here, puts us in our update lights function. All right, so if we look here, it says apply delta time to light fading. Make the light shrink behavior time-based instead of frame-based. All right, so we're targeting a specific light in our array, and we're targeting its radius, and we're saying we're subtracting off our light shrink rate. Okay, so not really sure what we need to do here. Let's think about this. So right now, light shrink rate. We're subtracting off light shrink rate. So this is sort of like a speed. And we saw in our previous mission, we took a speed and we multiplied it by a time. So we have dt. Let's multiply by dt and let's see what happens. So I'm going to take that rate, which is just another way to say a speed, and we're going to multiply it by dt. Let's see. Oh, that doesn't fix anything for us. Well, why is this happening? I think this code is right. I think we fixed this, but we might need to head to mission number 5 to see what's happening. Because remember, we said that the shrink rate of our light was something that we were going to control with our difficulty ramp. It was not going to be a constant value anymore. In fact, we commented out the constant value and said that our ramp would control it, because at the start of our game, our lights would shrink slowly, and the longer we play, the lights would shrink faster and faster and faster, making the game more challenging. So mission 5, we have to define what our ramp constants are going to be. And if we look, what are they set at? They're all set at 0. So the light shrink speed start is currently 0. Our light's not going to shrink at all. I don't know. Let's just put a number in. I'll put in like, let's put in 100. If I change that to 100, will our light begin to shrink? Let's just see. And there we have it. Of course, that's way, way too fast. What was it before? It was 0.21. All right, so let's think. It was 0.21. That was frames per second. So assuming we were at 60 frames per second, I should set it to be about like 12.6. Okay, so let's do that. Of course, I don't like 0.6. I'm going to set it to 12.5. That makes me just feel a little bit more at ease. And before we test this, let's change our ramp time seconds. It's currently set to 0. Ramp time seconds is how long it's going to take for our ramp to get our game to its maximum difficulty. We're going to do it in 120 seconds. So after 120 seconds, we will be at our maximum difficulty. And how do we do that? Well, in 120 seconds, our light shrink speed is going to start at 12.5 pixels per second, and it's going to end faster, about 25 pixels per second is what I've got. Our enemies are going to spawn every 5 seconds at the start, and by the end, they'll spawn every 2 seconds. So we'll get enemies much faster. And our enemies are going to have some base speed, and we're going to multiply that base speed by 1 at the beginning. And by the end of the game, we're going to multiply that base speed by 2.5. So they're going to be moving 2.5 times as fast. So those are going to be our ramp constants. So let's check this now and see if that fades a little bit better. Oh yeah, that's like exactly what we had, I think, originally. So this is really great. Our time-based systems are working. Runtime seconds, our health, our movement, and our shrinking of light zones is all in effect. So now mission 5 brought in this idea of our ramp constants. We are going to use these to control the difficulty of our game. So let's build this out a little bit more. Mission 6 brings us to a function called update ramp values. Where are we calling this? Well, if I scroll up a little bit, inside of our draw function, which gets called every frame, if we are in our play mode, look at what we do. We update ramp values, and then we update our player, our lights, and our health. So every single frame of our game, we are going to update these ramp values. So what exactly is a ramp value? What is a ramp value? I have no idea. Well, I think we saw a ramp already. If I come up here just outside of my student edit zone to my gameplay variables, see, we introduced runtime seconds, and then we introduced these variables. Ramp was 0, light shrink rate was 0, enemy spawn interval was 0, enemy speed multiplier was 0. And then if we go to our reset game to defaults, anytime we reset a game, the ramp goes back to 0, as does runtime seconds. So runtime seconds going to 0, that makes sense, because when I restart my game, it goes back to 0. So that's good. But all of our ramp values get set when we reset. Our ramp goes to 0. The light shrink rate is no longer 0. It's our starting light shrink speed of 12.5. Our enemy spawn interval is no longer 0. It's our starting enemy spawn time of 5 seconds. And our speed multiplier is no longer 0. It is our starting speed multiplier of 1. So somehow we have to take these values that we start at and bring them to our ending values. Where are our ending values? Right? When we define these, we defined them right here. We somehow got to get this number to this number, and this number to this number, and this number to this number, and we have 120 seconds to do it. Well, mission number 6 is the start of this. We have to build the ramp. So let's head over to the whiteboard and let's discuss what the ramp actually is. So our ramp is going to be a number. So let me just write this over here. Our ramp is going to be some number between 0 and 1. So it could be like 0, it could be like 0.15, it could be 0.3, it could be 0.5, it could be 0.89, it could be 1. Any of those values. All right, and now imagine we're going to use those numbers to determine the difficulty of our game. So this is max difficulty, and this is minimum difficulty, max difficulty. Right here at 0.5, that's like the midpoint, right? So we would say medium difficulty. So how do we do this? Well, imagine I created a graph, and on one end of the graph, I put these ramp values. So right here, I'm going to put 0, zoop. And right here, I'm going to put 1. That's my ramp. On my other axis, I'm going to put a value that we are going to control based on the ramp. So let's do our shrink speed. So our shrink speed, when we start the game, our shrink speed, what did I say? I think it starts at 12.5. And when we end the game, it ends at 25. All right. And so what we're going to do is when we start the game, our ramp is at 0 at the minimum difficulty. So our shrink speed is 12.5. And at our maximum difficulty, when the ramp is 1, our shrink speed is going to be all the way up here at 25. So there's our starting point. There's our ending point. Imagine if we were to draw a line between those 2 points. We can get any value for our shrink speed. Right? It's going to get bigger and bigger and bigger as we go along here. What moves us along this line is our ramp. So when our ramp has a value of, say, 0.3, our shrink speed is going to be higher. Maybe it's like, I don't know, 16. And when our ramp has a value of 0.5, it's going to put us right here. I don't know what this is. I probably should know this. I'm just going to take a guess. I'll just say 18.5. All right, it's going to go up. And when our ramp is at 0.89, maybe it's going to put us right here, 0.89. All right, so now our shrink speed is even faster. Maybe it's 23. And when we hit maximum difficulty, we said our shrink speed is at 25. This can be done for any of those values. It could be done for our shrink speed. It could be done for our spawn rate for our enemies, or how fast our enemies move. And this idea of moving from a starting value to an ending value over a range of 0 to 1 via some line like this is known as linear interpolation. And we have a special way to say that in game development. It's called lerp. We're going to be lerping. All right. Not to be confused with LARPing. We are lerping here. All right. So let's take this idea and let's head over to the computer screen and let's see if we can build our ramp. So we need a ramp, something that is going to be between 0 and 1 to control our difficulty. Well, I think what we're going to do is we want to control it based on time. So we're going to use a fraction, and I'm going to use, let's see, runtime seconds, which is a measure of how long our game's been playing. It starts at 0, and I'm going to divide it by ramp time seconds, which is how long we wanted it to take for our game to reach maximum difficulty. So if you look, when runtime seconds, when our game starts, this is equal to 0. 0 divided by 120, well, that's 0. So that would be our easiest part. That's like everything's going to be right here on our graph. And then as the game runs on, let's say we get to 60 seconds. So 60 divided by 120 is 0.5. So that's going to put us at this point on our difficulty curve on our ramp. And then when it hits 120 seconds, 120 divided by 120 is 1. Not 0.1, it's equal to 1. So that's going to hit us at our maximum difficulty. But there's just one problem. If we don't die right here, our runtime seconds is going to get bigger. And imagine it gets to like 240 seconds. Well, 240 divided by 120 is 2. And if you look at our graph, I don't have 2 over here. The graph stops. So this is going to be really bad. We want to make it so that the largest value we can get for our ramp is 1, and the smallest value is 0. And this is a perfect way to use the constrain function. We've seen this time and time again. We're going to constrain this ratio, and we're going to say your smallest value is 0, and your largest value is 1. And just like that, we have created a ramp that we can use for linear interpolation to create this line between a starting value and an ending value. So mission 7, I can see it right here. It's about our light shrinking scale. It's all about lerping. So let's go to mission 7. We want to use lerp to scale the light shrink rate. We're going to increase pressure smoothly based on the ramp. So you can see we're lerping some other values like our enemy spawn interval and our enemy speed multiplier. Mind you, we don't have enemies yet, but we're putting the system in place so that as we spawn them, they spawn quicker and quicker and quicker, and they move faster and faster and faster. So we got to do something similar for our light shrink rate. I think that was the variable we had defined. Yep, light shrink rate is equal to, we're going to call the lerp function. Now, when you lerp, when you do linear interpolation, you have to provide the starting value and the ending value. Our starting value for the light shrink rate is going to be light shrink speed start. I think it's this second one. Yep, light shrink speed start. And then our ending value, when we're moving the fastest, is going to be light shrink speed end. And then you just have to specify, so those 2 points are going to define this line for us, zoop, zoop, that line, and then you just got to give a third number that tells you where on the line you want to be. Well, we do that via our ramp, and we had calculated that ramp in our earlier mission number 6. So with that, we have accomplished our first linear interpolation. Let's check it out. Let's see, is our light shrinking faster and faster and faster? I mean, it's hard to tell, right? I think our max gameplay, we have it at 120 seconds, and I'm only like, 13 seconds in. I guess I can sort of see it. Let's go mess with our ramp constants. Instead of having our light shrink speed end at 25, let's end it at, 500. So now it's going to end super, super fast. And so in the, 15 seconds I'm alive, we should really hopefully see it. Oh yeah, I can, oh, there you go. You can see it speeding up right there. So that worked out really nice. Of course, we don't want 500 seconds. So I'm putting that back to 25. But that brings up an interesting idea. So we're building a system that we can't fully yet see the effects of the system. So how do we know that it's working? Well, if we go to mission number 8, mission number 8 is all about a ramp display. We are going to display a ramp readout clearly in the HUD. So if we look here, we're in the draw HUD function, and we want to display some information about our ramp so we can read out these values. If I scroll down just a little bit, I have a function called draw ramp readout. And this function gives me all of the information about the current state of the ramp. It gives me the ramp's value, the shrink rate, the enemy spawn interval, the enemy speed multiplier. So we should be able to see those values on the screen changing in real time as our game plays. And then we can simulate the difficulty getting harder and harder and harder. All I need to do is call that function here. So draw ramp readout. 2 parentheses to call that function, and a semicolon for good JavaScript. And that should end our lesson. If we run over here, now when I refresh my game, I get my ramp percentage, my starting shrink rate, my starting spawn interval, and my speed multiplier. As soon as I hit enter, as time goes on, the ramp is going to increase, getting closer and closer to 1 or 100%. The shrink rate will go up, it'll increase, the spawn interval will go down, and the speed multiplier should go up. And there you can see it happening. So as our ramp gets bigger, our lights are shrinking at a faster and faster rate. Our spawn interval is dropping, so now they spawn every 4.7 seconds, and our enemies are going to be moving faster and faster. All right, and then oh no, there's no chance. I'm dead. But this is a wonderful place to stop. We have effectively taken the frame-based game over here and switched it to the time-based game over here. And that is going to help us out so much because now our game will play consistently on any machine. Given this new time that we've created, we built a ramp system that allows us to scale our difficulty the longer we play the game. And we don't do it through difficulty spikes. We do it smoothly through a process known as linear interpolation. We've got a system in place now for enemies to spawn into the battlefield, and we can spawn them at given time intervals and have them move faster and faster and faster the more we play the game. So I think this is a great place to stop, and I'll see you in the next video.